So what would you say for the first one, question 3? On 1, 2, 3. Did D? Did E? Okay. So
It's supposed to be a 2 or 3.
what is it supposed to be, Rich?
Oh, never mind, never mind.
I don't know what that line is. It should be 11 to
Yeah,
3.
that's why that line. Sorry.
Yeah, sorry.
I don't know where that came from.
Yeah, so we're going from 11 to 3. And that's gonna give it, we know that the final value is all we care about, so that's a Paschen series transition. And everything else is either gonna be higher in energy, like A and lower energy. Also D.
11 to
And why not 7 to 3?
11 to 3. Yeah, it's right. Lower energies, less energy.
Yeah, so let's just make this energy level 3. And we know for in C right here, we have 7 to 3, right? So we are here versus in D, we're 11 to 3. So we're up here. And we know this electron is either jumping down in this, going all the way to 3 like this, or it starts in this energy level, it goes down. So which one is going to have more energy associated with it when it, yeah, 11 to 3, right? Because you, like Rich said on Wednesday, you can think of it as a building. You're going to have more potential energy up here. When you jump down, you're going to end up having more energy or releasing more energy in the form of an electromagnetic radiation. So the answer is actually C, because they are both Paschen series transitions, right? So they're both IR, but which one's going to have a photon with less, emit a photon with less energy is the one that doesn't have the greatest difference in energy levels. So 7 to 3 is only a difference of 4, and 11 to 3 is a difference of 8. Are there any questions on that?
The answer is C.
The answer is C. Is that what you got originally? Nice. Why didn't you say it earlier?
Board.
Okay. Which of the following emits a photon with the largest frequency?
Our frequency, low wavelength.
Hey, think in here. You gotta let everyone else, you gotta let everyone think for themselves. You like a angular. Think about it. Who has an answer? All right, you got an answer? No? Oh, yeah. Okay.
I would pride.
All right. On 3. 1, 2, 3. Oh, we gotta. Wait, what did
Difference.
I said
largest frequency? We talk about highest or lowest. Is it going to be higher or lower energy? Higher energy, right? So we're going to be looking for something in the UV region, which is a Lyman series. And if that's not there, then we look for Balmer, and then we look for Paschen very last, right? So which one do we think? D. What did you say originally? What did everyone else?
I said
C,
D.
bro.
You said C.
I can't even see.
Can't even see D.
Like I can't even.
Oh,
Katie
Okay.
Lamb? What?
yeah. So the answer is going to be D, because although they are both, we agree that they're both Lyman series, right? So it's going to emit a photon in the UV region of the electromagnetic spectrum. Agree? Yeah. So now we're just looking for the one that has the greatest difference in energy levels or jumps, right? So this goes from 8 to 1, which is a difference of 7, whereas this one goes from 7 to 1, which is a difference of 6. So this electron that was here in energy level 8 had to jump 1 extra floor down. Therefore, it's releasing more energy. Thus, that photon is going to have a higher or larger frequency. All right. Yeah.
It is different.
All right, so let's do a quick intro review for quantum numbers. N equals, oh, you got this.
All right, so quantum numbers, right? Some Oppenheimer stuff. Dealing with the quantum stuff here. So quantum numbers, right? There's basically four of them. N, L, M sub L, M sub S. Here's the analogy. The analogy, right, everybody uses for quantum numbers is it's like the address of an electron. That's what everybody uses. So you have like your N, which is like the state you live in. So like we live in Texas, so that's our N. Our L, right, could be something like our county, like Bear County. Then M sub L could be like I don't know, the street you live on, like your street, and then M sub S, is your house. That's what everybody uses, right, for quantum numbers. So they get like more specific as you go down. So unfortunately, we can't refer to these as city, county, state, and whatever house. So we gotta talk in technical speak. So first quantum number here is N. N is referred to as the principal quantum number. And not even how you spell it. Okay. Principal quantum number. Like what J. Cole said, it's simple, it's a principal, yeah. Principal quantum number. So the N, right, is associated with your energy level. So if you all are familiar with electron configuration, you're doing like the 1s2, 2s2, like that's where this N comes from, right? The 1 and the 2s are like your N's, your electron shells. This is important. He does like to ask you a lot on like possible ranges for quantum numbers. So N can be any number from 1 to infinity. Now on the periodic table, this might be a bit confusing because on the periodic table, we found we've only found the highest N to be 7 so far. The highest one, the element we found so far, but theoretically, right, it can be 1 through infinity. So you can have in an ideal world, an infinite number of electrons, an infinite number of electron shells. So N is the principal quantum number, and it can be anywhere from 1 to infinity. Now, next, we have L. L is referred to as the angular momentum quantum number, or if you're taking the MCAT, they always refer to it as this, the azimuthal quantum number. That's just a fancy way for saying angular momentum. So this refers to your type of orbital. This is S, P, D, or F. It'd be a good idea as well to know what these shapes are. So an S orbital, okay. S orbital, right, is in the shape of a sphere. It'll look something like this. This is an S orbital. So S orbital, sphere. Remember it, S for sphere. P orbital looks like this. It's kind of like a dumbbell. So I don't know. People call it a dumbbell, but you just remember it like P for pump. So to get a pump in, you lift dumbbells. So P. D orbital. This one's kind of like a flower. So this one right here, and 5. There's 5 of these little points. Okay, it's a bad drawing of it, but this is the general shape. And F, don't worry about the shape.
Can't even draw it.
Oh.
Computer.
Well, you probably can draw it, but me personally, I can't draw it because I just messed up to probably get it like really accurate, yeah. But again, I messed up drawing the d orbital, so I probably need a computer for that too. So basic idea, right, is L can be any orbital, right, from, or it refers to your type of orbital, S, P, D, or F. So the range, right, for your L, these are the possible values. It could be anywhere from 0 to n minus 1. So 0 to n minus 1. So what's it called? The thing refers to like what the orbital is. So an L value of 0 would correspond to an electron being in the s orbital. An L value 1 would correspond to the p orbital, L of 2, D value, L of 3, F, so on and so forth. There, again, this might be a bit confusing. We've only discovered up until F for now. There's other orbitals out there like G, H, J, and those have other L values associated with them, 4, 5, 6, etc. For the periodic table, we've only discovered L equals 3. Remember that G orbital though, it might come up sometime on some assignment. So that is the G orbital, right? What's it called? I had a thought. All right, you all know what orbitals even are? What even is an orbital?
How the electrons spin, or how it goes around the.
There's something a bit more. Okay. Yes and no. Yes and no. So that's part of it, yes, but there's another part.
Alright, what did you say about the G orbital?
I said theoretically it exists, but yeah, remember it for an assignment. It's a little tip.
Where it takes.
Yeah, and the area you can occupy is probably like the closest way to get to it. So here's a formal definition, right? Orbital is a mathematical wave function that basically designates the area an electron can occupy. So basically, it says that for an s orbital, right? It can be the electron can be like anywhere within that sphere. The sphere is like its possible region of movement. The p orbital, this is a bit confusing, but the electron can be here, that region. The little region in the middle is called a node. That's an area of no electron density. So anytime you see a node, there's no electrons located there. The d orbital also has one in the middle there, but yeah. The basic point I want you all to get with, or we want you all to get with orbitals is that they're mathematical wave functions that determine where an electron can be. So onto that, m sub L, right? Your magnetic quantum number is your orientation of orbitals. So how your orbital sort of is like in real time. So let's take, for example, right, the p subshell. If you all remember electron configuration, right? Again, we go back to electron configuration. This is actually how electron configuration is made, but I don't know. I'm working backwards here. So we all remember how electron configuration, you go 1s2, 2s2, 2p6. Here's the thing about orbitals. An orbital can only hold, this is like the case for any orbital, by the way. S, P, D, or F, it doesn't matter. Any one orbital can only hold a maximum of 2 electrons. So only 2 electrons can occupy one given orbital at a time. So with that being said, we say 2p6, right? Where's the 6 come from? But an orbital can only hold a maximum of 2 electrons. Where'd the 6 come from? So like, we say 2p6, right? Like say you're doing like neon or something, electron configuration, it'd be 2p6, but there's only 2 electrons per orbital. Not really. So we only have 2 electrons possible here, right? In one given orbital. So if there's 2 electrons per orbital, and we have 6 electrons total in our p subshell, how many orbitals do we have? 3 orbitals. We have 3 total orbitals. That's how we're able to get 6 electrons for that 2p6.
The electrons are double orbitals, are they not?
Yeah.
Or the amount of electrons are double the type of orbital.
Double the number of them.
Like-
can be
Like 2D as 5
Yeah.
positions.
But you're getting a little ahead of where I want. That's correct, but yeah. So this value, right? These different orbitals possible because of the fact that your orbitals can exist in different orientations. We'll take the p orbital for example, because that one's the easiest. So there can be a 2px where the orbital is flat like this on the x-axis. Then there could be a 2py where it's vertical on the y-axis, or there could also be a 2pz, which like you can imagine it's 3-dimensional. So one half of the orbital will come out facing you, the other half will go into the plane of the board. So basically, this is where these 3 orbitals come from. And as David said, this does come from the fact that the M sub L range is negative L to positive L. The idea here is that each number covers a possible axis the orbital can be on. -1, for example, could be that orbital on the x-axis. 0 could be on the y-axis, and 1 could be on the z-axis. So, as David said again, the region for M sub L is the negative L value to a positive L value. All right, and as Colin was talking about, there is one final quantum number, that is M sub S. And the good thing about this, there's only 2 possible values, either 1/2 or -1/2, no in between. So if you see 4/8, is that a possible spin value?
Cause it translates, no, no,
Oh, I'm just listening.
cause it translates to 1/2, then
This is definitely not like math. So if you see, you need to directly see the number 1/2 in front of you. I don't care if it's what's it called, 2/4, 3, or what's it called, 8/16. I don't care. As long as you see number 1/2, that is a possible value for M sub S. So it can either be 1/2 or -1/2. And the 1/2 and -1/2 comes from the fact that an electron can either spin upwards, or spin downwards. So you can imagine, right? An electron is like a planet, right, orbiting the solar system. So the planet, right, it doesn't always like some planets, right, orbit the sun weird. Like like Uranus tilts on its side to orbit. Or the same thing here. When some electrostatic force, right? What's it called, the strong nuclear force, what they call it. So it's when an electron can either spin up or spin down. So it can either spin in like a clockwise direction or a counterclockwise direction. There's no in between. Like it doesn't like spin clockwise 1 second, counterclockwise the next, and then do all this weird stuff. All right. So that, in a nutshell, is quantum numbers. Let's do a little review. I want y'all to tell me whether this set of quantum numbers is possible. Like whether this is even a possible thing to do or not. Say n equals 5, L equals 3, M sub L equals -4, and M sub S is +1/2. Is this given set of quantum numbers possible? Raise your hand if you say yes, it is possible.
I think it's possible.
All right,
wrong.
Dylan thinks it's possible. Raise your hand if you think it's no.
No.
Raise your hand if you're unsure. Why are you unsure? All right, fair enough, I guess. So, N, right? Most of y'all got it right on the money. It is in fact no. So, for those of you who said no, where's the problem? Which quantum? Yeah.
L equals 3, M of L equals.
So I'll ignore the part about L equals 3. So, and jump to the M sub L equals -4. Why is that one wrong?
Because it's not the value.
So what should it be between? And what else? Yeah, -3 and 3. In this case, it's -4, not between -3 and 3. So why'd you say L equals 3?
Because the L gives you the three is not wrong, but the equation will be right if it's L equals.
Why would it be L equals? Why would L equals 4 be right?
because then M of L is or is in the range of -4 and 4.
Yeah, so you're exactly right, but you kind of misunderstood my question. I just wanted you to point out like which one was wrong. So, like which one of these, like, okay, given like the n value is right, given the L value is right, which one using like your rules doesn't follow? Yeah. So do you agree that L equals 3 could be a possible value for L? This scenario, yeah, you're exactly right. Can be.
You always gotta go like one step at a time, so. N values can only go from 1 to infinity, so this is an integer from 1 to infinity, so check, nothing's wrong here. Then the next quantum number is L, and that's kind of based off of the N value, because we know that L can go from 0 all the way to N minus 1. So if N is 5, then the maximum value that L can be is what? 4, right? Because the rules for this one is 0, any L value, as long as it's 0 to N minus 1. So 3 is in that range of 0 to 4, right? Then we jump to the next one. The rules for this one is it has to be from negative L to positive L, right? That's where the mistake is, because negative L would be -3 to +3, right? But we are outside of that range, we're at -4, so that's where if this is incorrect. This is right, and even this is right too, but.
How do we know the spin is positive?
But
How do we know the spin is positive?
so you don't like know, all right? It's not something you're gonna be able to figure out by looking at an atom or something.
You just, these types of equations. we
This
don't
can
care
either
about.
be positive or positive 1/2 or negative 1/2. It doesn't matter which one it
Those
is.
type of equations ask us, we don't care about spin.
You don't care about the sign, yeah. You only care is this 1/2 or not. Yeah, got it.
All right. Any questions on quantum numbers? Yeah.
I wasn't, might be like. Turn the video. I just said that you can find.
Oh, that's not speculation at all. That's exactly correct. So, no, it's just 2n squared. So, as David has introduced us to a new concept, so he does ask this too. So, let's just say, what is the max electrons in the n equals 4 subshell? So I want to know in my 4th energy level, what's a full electron shell gonna look like? And for that, as David said, use the good old equation 2n squared, where n is our principal quantum number. Yeah, that 2 is weird. All right, 2n squared. So again, where n is our principal quantum. So we're gonna plug in 4 to this equation. 4 squared is 16 times 2, so there's 32 electrons. Yeah, that's a true equation you got there.
My last video was Simon didn't show any pictures, which is audio.
That's kind of weird. You have like pop-ups enabled.
Yeah, it would just be a black screen and a motion. I don't watch the video on his YouTube.
You subscribe to his YouTube.
I'm so confident too, and I got it wrong.
Oh, what were you talking about with the four business? That 4
Monday?
something?
Oh, yeah, so she
Oh.
thought the equation. Sorry, but you on blast here. But she thought it was 2n squared times 2.
Oh,
I
4.
swear, like
You might be thinking of L, the L equation. You can use this for L two to figure out the maximum number of electrons. You can use it for L two. That equation has a 4 in it, but the easier one is using the 2n. Thank you, MCAT, for that. Alright, so essentially now, electron configuration makes sense. That's the whole thing of this. So with a full electron shell, basically, you'll have 32 electrons. This is including the S, P, E, and F. Alright. Another quick review. How many electrons are in an orbital? One orbital. Yep, there are 2 electrons, 1 orbital. How many p orbitals are there? 3.
What do you mean by one? How many electrons are in one? What's the first question?
How many electrons are in 1 orbital? Yeah, it's 2. That was a, yeah. You got it right. Alright, think of another thing. How many electrons are in? How many electrons are in an F subshell? How many electrons? The maximum electrons are in F subshell. 14. Exactly right.
Yeah, so if you ever are not sure, you know that the L value associated with an F subshell is what? 3, right? Because it goes from 0 to 1 to 2 to 3, where this is S, P, E, F, to 3. So we know that the possible values for M sub L, M sub L tells us all of the orbitals in that subshell, right? So M sub L, the rules are from negative L to positive L, right? So this would go from -3, -2, -1, 0, 1, 2, 3. We see that there's 7 different possible orbitals, and because each orbital has can fit the maximum of 2 electrons, 7 times 2 is 14 total electrons that can fit in the F subshell. That makes sense. That makes sense? Cool. All right. I don't think y'all are there yet.
Alright, what was the last thing y'all remember going over in the video assignment? One question about what?
How many electrons? We go ahead, we go.
Oh, Heisenberg?
Touched on barely.
My favorite movie.
One where like the more you zero in on locate position, then the other one.
The momentum, yeah.
How many
That's
occupy. Basically
Oh,
all we said
basically,
about that.
yeah.
Yeah, it's just more of an idea than anything. I don't think I've ever seen him test on like a calculation based question.
I mean, you won't start now.
Yeah, that is true. Doesn't mean that-
Just in case, what is the calculation?
what is the equation
What
for
is it?
Something over something. Four involved.
There is a 4 involved. I'm saying the equation for the Heisenberg. I'm sorry.
H over 4 pi.
P momentum?
H. Heisenberg goes to
So delta P refers to the momentum of the electron. That's mass times velocity. Delta X refers to the position of an electron, as that's a displacement here. And then this is greater than or equal to H over 4 pi. H being Planck's constant and pi being.
What this is just telling us a conceptual idea that what delta pi? What? Interesting. Yeah, so So what this tells us is that, say we know more about. Well, it's kind of hard to describe it in saying we know more about, but let's talk about an electron. An electron can move at some speed and have some momentum associated with it, and that's denoted as P, momentum. But we also know that these electrons are at a certain area in space, so that's gonna be their position. So position is denoted by delta X. But what Heisenberg's uncertainty principle says is the reason it's in inequality is that the more you know about one, the less you know about the other. So I don't know if y'all have ever heard that joke with Heisenberg. Like Heisenberg gets pulled over by a cop and the cop asks him, do you know how fast you're going? And Heisenberg replies, no, but I know where I am. He's like, well, you're going 70 miles per hour. And then Heisenberg responds, well, now I don't know where I am. So the more you know about one, the less you know about the other. That's the whole idea of Heisenberg's uncertainty.
So delta P is position, delta X.
No, delta P is momentum,
Delta X is.
position. It's a physics thing. Once you take physics, you'll be like, okay, this is where they assigned it. Because you can't assign momentum with the M because that was already taken by math. Well, that's what we think, right? But that's not because this is a physicist came up with this. And in physics, there's already a variable M for mass. So you can't have E or you can't have delta M because then it's going to refer to mass. So they came up and said, all right, P. It's probably something in Latin for all we know.
It's
For
not.
Greek.
Like the legitimate reason for the P is because M is already taken by mass, so the closest letter was P.
M, capital M, lowercase o.
Capital M is malaria though, and then lowercase o is something else.
Interesting.
Lowercase,
Particle nature of photons.
Oh, wait, is this not de Broglie wavelength?
First on mass times velocity. Oh wait, no. You can rearrange it for that. Never mind. Yeah.
Yeah, okay, so these are important things. So you did learn about de Broglie wavelength.
De Broglie wavelength.
So this,
By MU.
yeah, so what de Broglie came up with back in the 1920s was something. He basically came up with an equation that says every single piece of mass has a wavelength associated with it. And that's described by this equation where lambda, the wavelength, is equal to Planck's constant divided by the mass and the velocity of whatever that thing is. And we see that since mass is in the denominator, the larger the mass, the smaller the wavelength. And that's exactly why David's not dissipating out of this room right now, because David has relatively a big mass compared to the electrons. Thus, the wavelength for David is very small in comparison to the wavelength of an electron.
Still Heisenberg uncertainty?
No, this is de Broglie wavelength. Yeah,
Wavelength is P equals H.
yeah, so de Broglie and wavelength. So aside from all the shenanigans, what are the exceptions? Because I don't know if y'all realized, but you always get tested on the exceptions. Whether it was solubility rules, you're always going to be tested on an exception, not something super easy. So in terms of electron configuration, what are the exceptions for elements that have different electron configurations than you would expect? No, just elements like atoms, not neutral atoms.
I haven't gone over electron configuration yet.
We barely touched.
All right.
We don't know about like the 1s, 2s.
Quantum numbers. Question on that Darth Star Wars
The
question.
Jedi one?
Got it right, but it was still pretty like
The murder mystery one. wavelength.
That's a good question.
I know, he said that y'all were having fun with it.
Yeah. We got to talk with our neighbor. That's to remind Megan that we've been seeing wavelength already.
Oh, wow. How would she forget that? That's so embarrassing.
No, for real.
Where's she at right now, by the way?
She said,
Dang. Anyways, that's fake, whatever.
We give her a synthesis problem real quick.
Alright, so,
So delta P is change the momentum,
yeah, it's just changing momentum, but
and P is just momentum.
no, P is wait,
Yeah,
Yes.
yeah.
yes,
Yeah.
P is momentum, but we're not dealing with that. We're just talking about the change in momentum. But we refer to it as momentum, even though there's a delta sign there.
I remember like delta T was like final temperature minus initial temperature. The same thing here, like it's the final momentum of the electron minus the initial.
Yeah, so let's do a quick thing on electron configuration. So, does anyone have a brief description on what an electron configuration is? What does it describe?
Much just like. Fishing.
Pretty much, yeah. Have anything?
I mean, the way, go for it.
The positive, negative spin of an electron in each shell.
Yeah, if you were to do it like with the diagram, then yeah. But the way I was gonna say it was, it's a sort of a concise representation of like an electron in each subshell.
Yeah, so let's just start with the most basic, hydrogen. Hydrogen has, it's in the, what orbital subshell? It's in the S, but specifically what? 1s, right? So it's in the 1s. And we know from our quantum numbers that there's only one orbital in the 1s subshell, or in any S subshell, right? So we denote that 1s. How many electrons does neutral or just plain old one hydrogen atom have? Yeah, one. So we denote that with the up arrow, half-headed arrow. And when we see something like helium, let's go down or across the periodic table. What subshell do its electrons occupy?
1s.
1s. And now we know we have 2 electrons though. So we filled up that orbital. But let's take it a step further and jump to carbon. Yeah, so how many electrons does it have in its 1s orbital? 2, right? Because 1s is already filled up for carbon. Carbon is in the second period, therefore all the electrons that we add to it or remove from it are going to be in the second energy level. So what we see is its 1s is already filled. What's the next one that gets filled up for carbon? 2s, right? And this is all Aufbau's principle. And then we also have the 2p subshell. And how many orbitals are in the 2p subshell? 3, right? And this all comes from our quantum numbers. You'll just begin to realize that p subshells have 3 orbitals, and D has 5 orbitals, and then F has 7. So how many electrons do we have in our outer shell of carbon? Well, outer shell, outer energy level. That's how many electrons? I need a number here, just a number.
Well, how many electrons carbon has?
In its outer shell, meaning its second energy level. Okay, it has 2 in the S, right? Because carbon has 4. Yeah, it has 4 total, right? But we have to fill up the S first based on Aufbau's principle. And then we fill up this one. Now, do we do this or do we do this? This?
No.
This?
You're killing me, Dylan. You already did that.
Okay, yeah, so before we double up electrons, so double up is like 1 orbital here, and we have 2 electrons. This is not doubled up. Before we double up, we always add them to the next empty orbital, because think about it. think of this analogy of if you get onto a bus and most of the seats are full, but there's one empty seat. Are you gonna sit in a seat that's already has one other person in it? No, right? You're not gonna double up unless you have to. So same thing with electrons, especially because they have negative charge and they don't want to repel each other. So they're only gonna go into an orbital and double up once all the other seats have been taken. So that's for carbon. And
What's that rule called when you what he just said? What's the rule called?
Didn't say it was alpha.
Alpha is like you have to fill the lowest energy level and then work your way up.
Yeah.
Start with the H.
Let's start with an H.
Hendrix?
Okay.
No, that's a guitarist.
It's
No.
not AJ.
Isn't the antisocial quantum?
What?
Antisocial quantum?
Antisocial quantum?
Yeah.
It's an H followed by a vowel.
No, that's not it. It's Hun or Hun's rule. However, if you have some German and you'll say Hun's rule. But if you're just an average guy like me, the Hun rule. So Hun's rule states that an electron gets put into an empty orbital before it gets doubled up. Now that doesn't mean, but then Aufbau's principle says you fill the lower subshells or first before you go into the higher one. So let's think about this again. Carbon has four total electrons in its outer energy level. So that's encompassing the 2s and the 2p. You already put one here, so we need to put four more. Even though Hund's rule says you don't double up until you add to empty orbitals, that would, if we took that literally, without Aufbau's principle, we would get this. Right? But that's not what we see experimentally. What we see is that Aufbau's principle says, well, this one has to fill up before we start going to the higher energy level. So this should be like a y-axis that says energy level. So this is the lowest energy. This is an intermediate, and this is going to be the highest in energy relative to the other two.
Probably seen it on Alex, as a matter of fact, with an axis.
Yeah, so the correct way is to double up, complete the 2s subshell before we go to the 2p and start filling up. Now, when we start dealing with elements that are lower on the periodic table, it's going to be very difficult to write out every single orbital. So what we end up doing is actually, we have something called the noble gas notation. So normally people would say, well, carbon has an electron configuration of 1s2, right? Because it has 1s with 2 electrons in it. It has a 2s2. Yeah, 2p2. Now what we see is if you wanted to use noble gas notation, you would use the preceding noble gas. So what's the preceding noble gas before carbon?
The noble gas comes before carbon.
Yeah, the noble gas, like Rich just said, that comes before. Helium, exactly. So helium would put helium in brackets. And then you would start everything after that. So then it would be 2s2, 2s2, 2p2. How many lone electrons does a single carbon atom have?
Electrons?
2. So do y'all know about diamagnetic, paramagnetic yet? I don't know why he told me to teach this today. He was like, yeah, they already did this in class yesterday.
But here's a basic idea behind that, like bare bones, like minimum. So if you have lone electrons, basically. So if you have like lone electrons meaning electrons are like that we see in carbon. So there's like, they're not completely doubled up yet. So basically when that happens, these elements start to exhibit semi-magnetic properties. They're weakly magnetic, but they're still magnetic. And then it's the same thing here for, sorry. Paramagnetic is when they're like slightly strongly magnetic. Dimagnetic is when you have everything is filled up. So you have no lone electron. Like a noble gas, or even you could say a metal like zinc, as all of its electrons could. So when that happens, that's a dimagnetic species. These species aren't that magnetic. They have very, very small magnetic properties. if any.
Yeah, so what we see with metals that are aramagnetic, we see if you bring a magnet close to them, they start interacting with it. But if you have a diamagnetic metal, you bring a magnet close to it, it's just nothing's gonna happen. So that's just like a couple properties that are derived from that. But looking at.
He'll go into a whole like thing with that, like y'all do a bunch of problems, like, is this element paramagnetic, is this element
Yeah, so let's just jump all the way to a transition metal and do iron. Let's just do iron. Okay, so let's use noble gas notation. So what's the preceding noble gas for iron? Argon, right? So we know that it's gonna look something like argon. What do you mean, man?
52K.
Don't even worry about it. Okay. Just say I'm fairly popular back in the day. All right, so argon, and we are dealing with, you gotta look at the energy level. So that's really just asking what period is it on. And what we see is this is period 1, 2, 3, and 4. So we're in 4th energy level. So we start going with this. And this is the 4th, if this is the 4th energy level, then this is the 4s subshell, right? So 4s is completely filled because we have to fill it in order to get to iron. So you can write that down. So 4s2. And what row is this? So yeah, so this is the 3D subshell, because remember our D subshells start at energy level 3, right? So the first D block subshell is the 3D subshell. And we just count how many elements are in it. So 1, 2, 3. These are really electrons. 1, 2, 3, 4, 5, 6. So we have 3D6. Yeah, because we're only going to we're doing the electron configuration for Fe. So we stop there.
So all the transition metals are the subshell and everything on the right of the periodic table.
Yeah. And then everything down low is in the F subshell. Well, it's definitely possible to maybe get a question on it.
I mean, they're called blocks, like what you just said, so like the left is the S block, middle part, transition metals are the D block, the right.
And
Yeah,
Yeah.
zinc. So it's always the 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And the stuff on the right, P block, and then the lower part, F block.
British want to sell an exam? All right. There's not much else. Just because I know Dr. Sadeghi, has he even touched on electron configuration yet? You need to start going to Dr. Armand's class if you have time, so that way you can be on top of the material and not have to.
Come in like towards the end of the class, otherwise you're just waiting for all the questions.
Yeah, that's true.
Towards the end of class, then it goes over.
I mean, you could come for the questions, like just as practice.
Yeah.
Tuesday, Thursdays, 1 to 2:15 at time.
But we are gonna try to make a worksheet or an exam review for exam 3.
When is exam 3, like 2 weeks from now?
When is exam 3, guys? What's the exact date?
Ready for that 7 a.m. final?
It's 7.
Oh yeah, you gotta wake up at 7 a.m. to take final.
No, you have to be here at 7 a.m. to take the final. So you gotta wake up at
That's not 3, right? That's
what?
No, that's not exam 3, that's
No,
the final.
yeah, it's just final.
Exam 3 on November 30th.
where do we take
30?
the final?
November 30th.
You'll send out
And
something.
then
And then you got the final like 3 days later?
The final is on
Actually-
December 5th, 7 to 8:58.
7 days.
Yep. I do remember that.
Only 1 hour.
later.
7 to 8:50. So an hour
My
and.
final exam is September 5th.
December 5th, yeah.
You have,
You have a 4-day gap.
Oh, you gotta dress for
Last
success.
exams.
I dressed in a whole suit last semester.
No, you didn't.
Did you
So
actually?
when's the exam for you?
Look for Oakham too. And it's because I was like, why not? Dress for success. And I only missed one question.
Is.
But
Is ACS
it's because I dressed for success.
ACS doing Best Fest.
No, we are not doing anything for Best
I would
Friends.
visit.
What? You could come to the EEA booth,
Yeah.
Educate Excel Academy, mentorship program for middle school students at Rudder Middle School.
That are rep-
I wonder who's gonna have like the best food.
We're gonna have the best.
We're gonna have the best
Like
drinks.
people who are selling like nachos, like, I'm not stopping.
You should stop by our booth though, B5.
What do y'all sell?
We're selling avocado crust.
For what? For that one? Yeah.
Lemon, raspberries, your
Oh,
choice
I
of,
do like lemon.
your choice of toppings.
Yeah, your choice of toppings.
Such as,
Yeah, like.
Such as
Chamoy,
chamoy,
tahini.
tahine.
I don't know, we'll,
Oh my god.
MES thing. Global Brigade.
This guy, always with the global brigade.
not doing anything for the top scholars?
Are they doing anything?
Yeah, they're doing boba, but like, I don't think they're gonna have as much success as. There's actually a boba place on campus.
Yeah, fact.
that place sucks.
Is that the one
Hey.
that?
I don't think I've ever heard anybody have a good experience there.
That's the one in the
Place
SED.
Place here or like?
Yeah, the place here.
I don't think,
I went. 'cause
I've
I
never
was-
gone to the one on campus, but I've gone to the actual Boston Tea.
Oh, okay, maybe that's better, but the one on campus is bad. I was so excited and I went. It was horrible.
Yeah, you got a bunch of children making boba, like, what do you expect? That's everything.
The one on campus is pretty neat. Had it like one.
Oh, I better see y'all there.
What time does it start?
Starts at 4, but it's all the way till 11, so you can really club whenever.
There may or may not be a reward.
Yeah,
Bonus points on the next
Bonus
exam. Bonus points on the
I
next
mean,
exam.
y'all get way more extra credit than we ever did.
How much did y'all get?
Dude, all
Oh
we
my
did,
god,
all,
actually, I don't even wanna talk about the exam.
all we had.
I
was
mean,
the
you could see me humiliate myself.
That's it, we didn't have.
Wait,
Alex
we can use
Coin.
Alex coin. So confused about that.
Were you in Armand's class?
Yeah. I
Okay,
have,
I
so,
think you missed the deadline.
that's fine, you can,
Late last week.
I thought you could just email like whatever, which
Yeah, but Rich said he had to email by like the 7th.